very much for this possibility.
Hold on just a sec. Good afternoon, good morning, good evening, everyone. So we're glad to have everybody back for our seminar on sheaves and complexes. And today we will have Irina Lanskikh. Sorry if I... Lanskikh. To talk about a new series of moduli components of stable rank 3 bundles on rational Fano threefolds. So please, Irina, go ahead.
Thank you for this possibility. I will talk about new infinite series of moduli components of stable rank 3 bundles on rational Fano threefolds of main series. Let me introduce the subject. We consider the Gieseker Maruyama moduli scheme of semistable rank 3 coherent sheaves with fixed Chern classes on rational Fano threefolds of the main series, including projective space x1, the three-dimensional quadric x2, the intersection of two four-dimensional quadrics x4, and the linear section of the Grassmannian x5. We construct an infinite series of irreducible components of the spaces of rank 3 locally free sheaves. And this is a joint project with Alexander Tikhomirov. Here you can see the exact references to the papers that I will mention later. I continue. We denote by M sub x RELP the Gieseker Maruyama moduli space of semistable coherent rank R sheaves on the Fano threefolds mentioned above of the normalized first Chern class C1 equal E, where as usual minus R plus 1 less or equal E less or equal 0. And the second and the third Chern classes are integer. Previously, examples of components of moduli or semistable sheaves rank 3 on Fano threefolds were constructed in the following papers. First, Benjamin Schmidt had constructed in 2023 for each value of C1 an infinite series of moduli components of rank 3 sheaves on P3. The sheaves, these sheaves are probably stable, at least one of such series, but this statements need proof. Second, Kamaski and Payensi in 2025 had constructed an infinite series of moduli components of stable instanton bundles of given rank greater or equal 3 on x1, x4, and x5. calculating the Chern classes, it's easy to see that our series differ from mentioned above. In this work, we study the geometry of moduli space M sub X 3E LP of sheaves of rank R equal 3. We construct it on X equal X1, X2, X4, or X5. Any series of moduli components of bundles different from the above mentioned families. Vasilyev and Tikhomirov in 2024 constructed on each of the above mentioned Fano varieties a new infinite series of reducible components M sub K M N of the moduli spaces MX to ELP. Most of them are rational and are realized as projectivizations or Grassmannizations of certain vector bundles over projective spaces. Okay. We proceed now the construction of our infinite series of reducible components of the moduli scheme. We have a small mistake, M sub X, 3ELP of rank 3 sheaves, in which a general sheaf is locally free. The idea of the construction such sheaves script E equal script E sub E comma xi of rank 3 is to define them as non-trivial extensions of the form 0 to O sub x minus A to script E to 0 for is a positive integer, where E is a general rank 2 sheaf belonging to the component M sub KMN mentioned above. Okay. And our main result is the theorem that on each of the Fano varieties, our Fano varieties, there exists an infinite set of couples of integers A, K, M, N, for which as the extension 1 gives a rank 3 sheaves E that form open dense subset of reducible components of the moduli space. And we have another result which has the qualitative nature, that the above constructed sheaf script E are generically locally free for any admissible couple A, K, M, N. Sorry, I didn't understand.
Sorry, it was just a leaked audio, so it wasn't a question or anything. Please go ahead.
We start with
continue.
Okay. We start with the study of singular points of the selected class of rank 3 sheaves script E. As we noted above, this class of sheaves consists of non-trivial extensions of the form 1, in which the rank 2 sheaf E are general sheaves in the irreducible components M sub K M N, constructed in the paper of Tikhomirov and Vasilyev. Let me recall that these components is described as the closure of the open subset. The subset of sheaves of classes of sheaves E, where E is a stable extension of the form 0 to O sub x minus n squared to E to O sub s of m to 0, where S is a section of O sub x of k, k greater or equal 1, n equals the scaling of k divided by 2, m plus n less than 0, and v is the Mukai vector of E. We know from paper 1 that sheaves E are stable. And henceforth we consider the sheaves script E sub E comma xi for non-trivial extensions 1. I write extension 1 here. We consider E from M sub K M N star, where M sub K M N star is an open subset of M sub K M N, consisting of reflexive sheaves. And for such E, by definition, E have only general E have only simple singularities x1 x2 xc3, where C3 is the third Chern class of E, and let Z is the set of these singularities. In order to prove the stability and study the singular points of the sheaf script E, we will need the following lemma. Let X be one of our Fano varieties, and let E from M sub K M N star, then first the sheaf home script E sub Z A comma E is just E minus A, and the sheaf x1 script E sub Z A comma E is just the sheaf X2 direct sum for X I in Z K sub Xi comma E, where K is the base field. Second, let us denote by small h the dimension of the cohomology of corresponding sheaf. So second, h1 of the sheaf home script E sub Z A comma E equals 0, and h2 of the sheaf home script E sub Z A comma E less than C3 of E for very big minus M. And the third statement is that the sheaf X1 script E sub Z A comma E is just the direct sum of K sub X I and H0 of the sheaf X1 script E sub Z A comma E is just the 3 of E. This lemma is proved using direct calculations using our exact triple from the definition of E, excluding inequality from statement 2. The inequality is proved by asymptotic reasoning. By this third statement from lemma 1, there are defined projections from the sheaf X1 script E sub Z A comma E to K sub Xi. And now we can define compositions named delta E from the group X1 script E sub Z A comma E to K sub Xi by the following way. Where delta is the homomorphism in the exact sequence 0 to X1 script E sub Z A comma E to H0 the sheaf X1 script E sub Z A comma E to H2 the sheaf home script E sub Z A comma E. And from the second and third statement from lemma 1, we have that H2 of the sheaf home script E that sub Z A comma E less than H0 of the sheaf x1 script e sub z a comma e for very big minus m. And therefore, the morphism delta is non-zero. And we have that the set OE defining by the following way. This is the set x1 script e sub z a comma e without the union of the kernels of delta e. Is a dense open subset of x1 script e sub z a comma e. So we have U script E is a dense open set in x1 script E sub z a comma e, and the sheaf E tilde defined as the extension epsilon 0 to e to script e tilde to script e sub z a to 0 is locally free for any epsilon in U sub e. In short, the proof uses Serre's construction. And as a consequence of these properties, we obtain the first theorem that under the previous assumptions, the following holds. First, for a general extension epsilon in triple 3, the sheaf script E equal script E tilde dual is locally free and satisfies our triple 1. And the first and the second statement that for A in range 2 3n minus 4, the sheaf script E is stable. The proof of the second statement use the mutability criterion for rank 3 sheaves on our Fano varieties, which states that a normalized rank 3 sheaf if is mutable if and only if it's zero cohomology and zero cohomology of its dual twisted are zero. Now we are able to compute the dimensions of the families of our shapes. Consider the family tilde T sub A K M N of all sheaves script E sub E comma xi, satisfying the hypothesis of theorem 1. It means that tilde T consists of pairs E comma xi, where E from M sub KMN star and xi in projectivization of x1 e comma or sub x minus a, where psi dual from the projectivization of u sub e. And we have a natural morphism, pi forgetful morphism from t tilde to m sub kmn star, which maps a pair e comma psi to e, such that t tilde sub akmn is a dense open subset of a projective bundle over m sub kmn star with fiber projectivization of x1 script e to o sub x I have a mistake, not script, just e. E comma o sub x minus a over an arbitrary point e. Hence, we have a formula for dimension of t tilde. It's equal the dimension of m sub kmn plus x1 e comma o sub x minus a minus 1. And by theorem 1, we have the modular morphism phi from t tilde to m sub x u, where u is the Mukai vector of script e, and a pair e comma psi maps to script e. Let me give more definitions. Let script m bar sub a kmn be the closure or in m sub x u of the set t tilde sub a kmn regarded as a reduced scheme. And let script m without bar sub akmn be the maximal dense open subset of script m bar contained in the image of phi. And let t sub akmn is just a pre-image of script m. It follows from the extension 111 that phi from t sub akmn to script m sub akmn is a composition of an open embedding and a projective bundle over script m sub akmn with fiber projectivization of the sections of script e a over each point script e from script m sub akmn, and t sub akmn by definition is a dense open subset of T tilde sub AKMN. Together with the equality star, I just recall that equality star is the formula for dimension of T tilde. Okay, and now we can compute dimension of script M sub AKMN. This is the dimension of M sub AKMN plus x1 e comma or x minus a minus h0 of script e a. Okay. And now the computations using the above relation and the triple one yield our main result. Theorem 2. The varieties script M sub AKMN for n greater than 3. K equals the scaling of k divided by 2 and a in range n plus 1, 3n minus 4, and minus m greater than 0, a smooth open subset of the reducible components script M bar sub AKMN of the Gieseker Maruyama moduli scheme M sub X U, where X is one of our Fano varieties, X1, X2, X4, and X5, and U is the corresponding Mukai vector. Okay. And in the last, I have a sketch of the proof. It's sufficient to verify for an arbitrary sheaf E from script E, mistake, from script M sub AKMN, the equality that the dimension of script M equals the dimension of the risky tangent space of the moduli scheme M sub X U at point script E. By theorem 1, the sheaf script E is stable, so we have that the risky tangent space of the moduli scheme M sub X U is just x1 script E comma script E. Therefore, by equality A, it's sufficient to verify the equality small x1 script E comma script E equals dimension the dimension of script M sub AKMN for the admissible values of AKMN. Observe that since script M sub AKMN is a subset of M sub X U, and according to B, we have inequality that the dimension of script M less or equal that small x1 script E, comma script E. And thus the verification of equality C is equivalent to that inequality that a small x1 script E, comma script E less or equal that the dimension of script M sub AKMN. And the computations show that this inequality is true under the above constraints. It means for R in range n plus 1, 3n minus 4. I think that's so.
Thank you very much, Irina. Are there any questions? Irina, can I please ask you to show equation 1 again in the beginning of your presentation?
Okay.
What is the...
Here. In the end of the slide.
And then this E, not the script E, but the normal E, is one of these reflexive sheaves in the capital M.
This is reflexive sheaves in M sub KMN.
Okay, so this N is the number of singularities. Okay. In the sheaf.
No, the number of singularities is equal C3 of normal E.
Okay, and then this N is not C3. This N is something else.
Yes, this N is not C3.
Okay.
We have a formula for C3, but this is very big formula.
Ah, okay. And also, I missed, at some point you said that the curly E tilde is locally free. Is that true? Maybe in slide 10, 9 or 10? Yeah, there.
Yeah. Script E tilde is locally free, and in theorem 1, we have that for general E, for general script E equals script E tilde dual, where script E tilde is from triple 3. Triple epsilon is dual for triple psi.
Yeah, then I guess I missed, what is the Z, the definition of the Z?
Z is the set of singularities.
Z is the set of singularities for the normal E.
Yes.
Okay, good. So it's 0 dimension. So otherwise the E tilde could not be locally free. Okay.
Yes.
And do you know what happens when the A is not in this interval that you put between n plus 1 and 3n minus 4? in your last slide. So your last phrase is the computation showed that this inequality is true under the constraints.
No, we have the result only for this A, and our proof don't work for another.
Okay. Because you say that these, some slides back, you said that these sheaves are stable when A is between 2 and this 3n minus 4. Yeah, this item 2.
Yes, in theorem 1, we have an upper bound for A, and the left bound in proof of theorem 2.
Ah, okay.
Can I ask a question?
Sure, Dimitri, please go ahead.
Yeah, so you considered x1, x2, x4, x5. So these are what is called Del-Pezzo varieties. They are of index 2?
No.
So what are these varieties, x1, x2, x4?
Fano varieties of main series. X1 is a projective space. X2 is three-dimensional quadric. X4 is the intersection of two four-dimensional quadrics, and X5 is just Grassmannian, the linear section of the Grassmannian to 5.
And why didn't you exclude the cubic from this series?
Because in paper of in Tikhomirov and Vasilyev paper, we don't have a result for X3, but we believe that similar arguments we can apply to X3.
We have a small comment on that. Actually, we in our paper with Vasilyev, we just looked at rational Fano varieties. That's why we excluded cubic from our consideration. But actually, the method which we developed there works completely well for cubic also. So in our project, our current project with Irina, we are going to include cubic into this paper, into our project. And only we should check whether the constraints for A are the same for the cubic. So it is funny, but this works for cubic also, though it is not rational. And Dimitri asked about index. The X4 and X5 have index 2 in our series, and also cubic has index 2. But quadric and P3 have indices respectively 3 and 4.
Yeah, I understand. It's also interesting. Do you know anything about has anybody applied this idea to construct vector bundles on Fano varieties, just pulling back from some covering of P3, for example? So,
we did not. At least we did not do that. Of course, one could look for pullbacks of bundles on P3. Maybe, I don't know, maybe stability works. But what about moduli equations? Whether the pullbacks constitute a component.
So yeah, the pullbacks might deform to some other types. Okay.
Yes, yes, yes.
Did you check? Thanks, Dimitri. Did you check if these sheaves are instantons or they are not instantons?
They are not, definitely not instantons. Just compare Chern classes, compare our formulas and those for instantons. They are completely different.
Okay. And
something.
I could say one more word about the families which Schmidt produced. He actually, at least one of his families generically gives again family of locally free sheaves. In rank 3, that was our main aim. I mean, to find locally free stable sheaves of rank 3 constituting infinite series.
okay. Christian, you had a comment or question?
Yes, I was wondering if you know or you already tried to perhaps construct some rank 4 using now this new rank 3 and taking new extension to rank 4.
May I say that it will be our we think of this and a good example is produced by Schmidt for rank 4 sheaves. So he produced also families of moduli components of rank 4 sheaves. So his paper ranges up to rank 4. And whether this works or not for Fano varieties is a question for future study.
Okay, thank you.
Thanks, Christian. Maybe one more question. Did you try to look at the Serre construction for these rank 3 sheaves? Right, Serre construction is 2 sections of the bundle or a suitable twist of the bundle, whose co-kernel is the ideal sheaf of some curve. And what curve is that?
Actually, in our case, we look at extension like this. This is extension number 3. Irina, please open that page.
Okay.
Yes, this is it, where it is not definitely the same as you suggest, but still at the left hand we have rank 2 sheaf, but on the right hand we have the ideal sheaf of the set of points. So it works in our case just in this way, but not in usual Serre construction.
Okay.
when taking two sections.
Mhm. Yeah, just perhaps an alternative way to characterize these sheaves would be to see what kind of curves on X they correspond to.
Why not?
Yeah, why not? Right. Thanks, Dimitri, Irina. Any more questions from anyone? Questions or comments? If not, let's thank Irina for her very nice presentation.
Thank you very much.
And I'll stop recording.